Okay, today we are going to talk about a very specific type of one-dimensional motion where our acceleration is still constant, and that is called free fall. Why does it keep wanting to write in yellow? There we go. Free fall motion. So in this thing, things are accelerating due to gravity. If they're on their way up, they are going to slow down. If they're on their way down, they're going to speed up. So we are dealing with constant acceleration. Which means that the kinematic equations apply. And this constant acceleration on Earth is a very special number. It's negative 9.8 meters per second squared. And it is abbreviated with a G. So acceleration on all of our free fall problems is going to be G, and on Earth it's going to be negative 9.8 meters per second squared. On the Moon, on Mars, on Jupiter, that number is going to be different. But on Earth, all objects are going to accelerate in the absence of air resistance, because we're going to ignore air resistance for the time being, at negative 9.8 meters per second squared. All right? Now, we said that the kinematic equations apply, but there are some changes that we have to make, because we are now talking about vertical motion, and now we know the acceleration at every instant. It's g, negative 9.8 meters per second squared. So in some ways these problems are easier because we never have to solve for acceleration, but in other ways they're more difficult, and we're going to see some examples. So let's see the changes that we have to make. A is equal to g in every case. We have to change our x naught and x final to now y naught and y final, because the object is going up and down. So in that case, let's see here, we've got v final is equal to v naught plus g times t, replacing the a with the g. We've got y final is equal to y naught plus v naught t plus 1/2 gt squared. And we've got v final squared is equal to v naught squared plus 2 times g times y final minus y naught. So these then are the kinematic equation versions for free fall, and that's what we're going to be using. So now let's go ahead and take a look at some example problems. Okay, for example problem number 1, let's assume that we have a ball, and that ball is 20 meters above the ground, and it starts from rest. So we're just dropping a ball from rest from a 2-story building, and there are lots of different questions that we can ask. Let's say we want to know how long is the ball in the air for, so we want to solve for the time. Let's say we also want to know how fast the ball's going when it hits the ground, so what is the v final? Now for these problems, I am going to ask you guys to set up your variable table similar to what we did for horizontal motion, keeping in mind that we've got y naught and y final instead of x naught and x final. So we set it up y naught, y final, v naught, v final. And now we don't need to put a because we know what a is. Every single time it's negative 9.8. We can just write t. So we have 5 variables now instead of 6. Now we need to be very careful in terms of our positive and negative signs with vertical motion. Remember that in vertical motion, positive means up and negative means down. Okay? So we also need to be very specific about where our origin is. Most of the time, we're going to put our origin, y final, here in this case, at 0. All right? So we can fill out some of the chart here. Y naught, we know, is plus 20 meters because the ball starts out 20 meters above the ground. Y final is 0 meters because it ends up on the ground. The initial velocity is 0 meters per second, and the final velocity and time are unknown. So now let's see here. We can go ahead and solve for one of these. Is it going to be easier to solve for v final or for time? Think about it for a second. So probably easiest here is to solve for time right off the bat. Because we have that kinematic equation, v final squared is equal to v naught squared plus 2 times g times y final minus y naught. We don't need to know time in order to solve for v final, so let's plug in what we know. We're solving for v final. Remember, that's squared. That's important. We know v naught. It's 0 squared. That's easy math. 2 times negative 9.8. Again, that negative value is very, very important. And we are multiplying that by y final, which is 0, minus y naught, which is 20. So there are the numbers. And let's see here. We end up with v final squared is equal to 0 squared is 0. We have negative 9.8, which is 19.6. Oh, let's erase that and start over. (19.6) times negative 20. And throwing that into the calculator, we get 392. But remember, that is squared. So 392 is equal to v final squared. We then have to take the square root of both sides. So v final is really the square root of 392, which, taking the square root using our calculator, gives us 19.8. meters per second for v final, which is pretty fast. That ball's going over 40 miles an hour when it hits the ground. That's quick, but the acceleration due to gravity is quite large. 9.8 meters per second squared is a big acceleration. Now, if we know v final, we can go up here and fill in v final. It's equal to 19.8 meters per second. Oh, and I'm forgetting something very, very important. 19.8 meters per second. Should this be positive or negative? Because remember, whenever we take the square root, we get plus or minus on that 19.8. So should it be positive or negative? We remember that the ball's velocity is going to be pointing downward the instant before it hits the ground. So this should be negative 19.8. That is extremely important. Now, the second question was, how long is the ball in the air? This becomes really easy to solve using this kinematic equation. V final equals V naught plus GT. And we end up with here, let's just quickly solve for T because that's what we're looking for. V final minus V naught over G after doing a little bit of algebra. And plugging in the numbers, we've got negative 19.8 minus initial velocity was 0 divided by negative 9.8. And when we throw that into the calculator, we end up with 2.02 seconds. So this ball falling 20 meters has a free fall of 2 seconds, a little bit more than 2 seconds. So that's a really easy free fall problem. Let's look at one that is much more complex. All right, for this example, let's say we've got a person standing down here, and this person chucks a ball straight up with an initial velocity of 10 meters per second. Oh boy, we've got all sorts of different questions that we can answer as a result of this. We can say, what is the hang time? So in essence, how long is the ball in the air? If the person throws it up and then catches it right back at the level that it was thrown from, how long is it up there? We can ask, how high does it go? What is the maximum position of the ball? We have other sorts of questions like, how fast is the ball going? 2 meters above the person's hand. We can ask, when will the ball be at some position, y equals 1.5 meters? So with this basic start, there's all sorts of information that we can look for. And there's one thing that can really help us out on these problems, and that's the symmetry of the situation. The ball is going to go up, reach some height, and come down. And we need to recognize the fact that the ball going up is like a mirror image of the ball coming down. So at some instant here, the ball is going to have an upward velocity. And what we need to recognize is that at that same instant on the way down, the velocity is going to be identical, just going in the opposite direction. So a lot of times we can use the symmetry of this situation to help us answer these questions. So let's talk about the very first question here, figuring out what the hang time is. And in order to do this, another really, really key thing that we have to remember about these problems is at the very top, the ball's velocity is 0 meters per second. That's how we're going to answer these problems. So in order to find the hang time, let's just find how long it takes for the ball to go from the person's hand to the very top of the flight. Then we'll just double that time, and that will be the total hang time for the ball. So filling in our chart here for this problem alone, we've got, let's see, y naught, we're going to call the person's hand 0 meters. Y final, we don't know yet. V naught, the person threw it up with positive 10 meters per second. V final, we said at the top, the ball's going 0. The acceleration we know is g, and the hang time is what we're looking for. And I'm going to put an exclamation mark to remind myself that I'm looking for the hang time. So actually this question is really easy. We'll use the easiest kinematic equation, V final equals V naught plus g times t. And again, solving for t here, just like in the last problem, we get V final minus V naught over g equals t. Plugging in our values, V final is 0, V naught is 10, and g is negative 9.8. So we see we get an answer really close to 1. 10 divided by 9.8. 1.02 seconds. That is how long the ball is in the air for the upward trip. So if we multiply that times 2, we get 2.04. And this, then, is the total hang time for the ball, all the way up. So now let's take a look at some of these other questions we can answer. How high is the ball? Alright, so now let's answer the question, how high does the ball go? And again, for this one, we want to simplify it by just considering the ball's motion on the way up. So from the person's hand all the way up to the top. Let's fill in our variable chart again. Y naught again is 0 meters. Y final this time is what we're looking for. V naught is still 10 meters per second. V final is still 0 meters per second because the ball stops at the top. And now we know what the time is. It's half of the total hang time. So the total hang time is 2.04. So we're going to say that the time for the way up is 1.02 seconds. So now for Y final, probably the easiest equation is the long kinematic equation. Y final is equal to Y naught plus V naught t plus 1/2 AT squared. Oh, and it's GT squared because we're doing free fall. So let's plug in some numbers here. We're solving for Y final. Y naught is 0. V naught is 10 times the time, which is 1.02, plus 1/2 of negative, and you get to hear an announcement.
Jim Pace, if you're in the building, please come to the principal's office. Jim Pace.
Times negative 9.8, that's G, times, we're going to have to put our 1.02 squared down there. So let's throw all of this into the calculator and see what we get for Y final. Alright, so I threw it in the calculator and I got an answer of 5.10 meters for Y final. So this ball attains a maximum height of about 15 feet above the ground. Which again makes sense. The person's throwing it at, let's say, a little bit more than 20 miles an hour, so it's not going to go super high. Alright, so we've now answered the question, how high? 5.10 meters above the ground. Now we could ask other questions like, how fast is the ball going when it's halfway up? Or when it's halfway on the way back down? Alright, so now why don't we go ahead and solve this problem. When is the ball at y equals 1.5 meters? And it's actually kind of a complicated issue. Because when we say when is it 1.5 meters, it's actually at 1.5 meters 2 times. It's at 1.5 meters on the way up, and then it's also at 1.5 meters on the way down. So remember again, we're asking when is it 1.5 meters above the person's hand, because that's our y equals 0, not at the ground. So this question is actually going to give us 2 answers. So let's go ahead and fill out our variable table. Y final is going to be 1.5 meters. Y naught is 0 meters. V naught is still 10 meters per second. Whoops, 10 meters per second. V final is actually unknown. We're not sure what it is. And the amount of time is what we're trying to solve for. So the only kinematic equation we can use is y final equals y naught plus v naught t plus 1/2 gt squared. And plugging in what we have here, we know that y final is 1.5 meters, y naught is 0, plus v naught is 10 times t, which is unknown. And let's go ahead and say 1/2 of g is 1/2 of negative 9.8, so let's subtract 4.9, because that's half of 9.8 times t squared. So actually here we see we have a quadratic equation. And we can solve quadratic equations lots of different ways. With factoring, if it's factorable, this one is not, we can use our calculators and plug this in and look for the zeros, or we can use the quadratic formula. Take your pick, either the calculator or the quadratic formula. I'm usually going to go with the calculator and just find the zeros. But in order to do that, first off, we've got to get this 1.5 over to the other side. So we have to subtract 1.5 to set it equal to 0. So we've got 0 equals, let's rearrange this kind of the way we're normally seeing this, negative 4.9t squared plus 10t minus 1.5. So if we're going to use the quadratic formula, we've got an a of negative 4.9, a b of 10, and a c of negative 1.5. Go ahead and solve this whatever way you want. I'm going to just show you what the answers are. Alright, so I went ahead and used the quadratic formula, and I came up with the following two answers. T equals 0.16 seconds, and t equals 1.9 seconds. And if we think about this, yeah, it totally makes sense because it's going to be 1.5 meters. Remember that the total height of the ball was 5.10 meters. And this guy's going to be at 1.5 meters pretty quick. So 0.16 seconds makes sense. And then also, the 1.9 seconds makes sense because remember the total hang time was that, 2.04 seconds. So 1.9 seconds, it's just before it comes back to the person's hand. If we had gotten something like 2.9 seconds, then we knew we did it wrong. If we had gotten a negative time here, then we would have known that something was wrong. So here is an example of where a quadratic equation actually is used in the real world in free fall problems with physics. So we do not throw out either one of these times. They are both correct answers for this problem. It is 1.5 meters above this person's hand at both of those times. So these two example problems are just a smattering of what you guys are going to be seeing in the textbook. So happy problem solving.